Hello. So in this video, we want to talk about molecular, ionic, and net ionic equations, and then do two examples that involves these equations in them. So one thing you have to understand is these equations apply for a double replacement equation. So you need to have two ionic compounds together mixed and eventually end up with two new ionic compounds. However, usually at least one of those products is going to be forming a precipitate. So a precipitate is a solid being formed when two solutions are mixed. So sometimes when you mix these two solutions, you end up getting one precipitate, or in some cases, you might get both products to be a precipitate. And to find out who the precipitate is, we have to look at the solubility table, which I will be providing over here. I have my own version here, but I know every textbook might have its own table, so you can refer to your table, whatever your school has or your textbook has, or you can even search online for some solubility tables and find some common precipitates that are formed. So take a look at this example, this picture over here. In here, two solutions are being mixed. Before mixing, both of them were clear and colorless. So there was no, meaning they both were solutions and soluble. However, as soon as they were mixed, now you all of a sudden you see a red precipitate being formed. So eventually this red precipitate is going to be sinking to the bottom of the container and forming a solid. So this is what we refer to as a precipitate. So this is my solubility table that I was talking about. The way this table is organized is that all the negative ions are on the left, the positive ions are on the right, and then you can match them and see which two combinations will form a precipitate and which two won't. So anytime you see the solubility of compounds being labeled as soluble, that means it's going to be remaining as in the aqueous form, meaning there's no precipitate formed. But when you see the low solubility in this table, you can tell that there's a precipitate being formed. So there's a solid form. So again, soluble means no precipitate. Low solubility means there's a precipitate being formed. Now, these are some examples of some ionic compounds. We want to apply whatever we see in this table to these questions, to these examples, and see which ones form a precipitate. So my suggestion is to taking a look at the negative ion first, and then match it with the positive ion. So first one has Br minus, bromide in it. And as you can see, bromide only forms a precipitate with three things. And with everything else, it's soluble. So therefore, with Na, it will be soluble. So it's going to be aqueous. Next one is Cl minus going with Ag positive. And as you can see, it should be forming a precipitate because Cl minus only forms a precipitate with three things and Ag plus is one of them. So therefore, this will be a solid. Next one is strontium hydroxide. Looking at hydroxide, you see with strontium, it will be soluble. So it's aqueous. But then calcium hydroxide, there's no showing of calcium in that box there for hydroxide. So therefore, it's going to be considered calcium positive. 2 positive is going to be considered as all others. So it's going to be low solubility. So it will be forming a precipitate. Copper 2 carbonate, it will be forming a precipitate because as you can see, all carbonate pretty much forms a precipitate with everything except for alkali ions H plus and NH4 plus. So therefore, that will be a solid and a precipitate. Next one is potassium sulfide. So that will be also aqueous because of the fact that sulfide, it's soluble with all the alkali ions. So technically speaking, all the alkali ions are always soluble. So if I see, as soon as I see a metal group 1 like Na, potassium, lithium, all of those in an ionic compound, I know they are soluble. So that's a quick way to figure out the solubility. Next one is lead to nitrate. So nitrates, as you can see up there, with everything, they're soluble. So it's going to be aqueous. Next one is ammonium hydroxide. So as you can see, hydroxide is soluble also with ammonium as well. So it's going to be aqueous. All right, now let's take a look at two examples here. So for writing molecular equation, ionic equation, and net ionic equation. So in the first one, these two ionic compounds are given to us. So first thing for us is to write the products of them. So we have to do the double replacement now and create two ionic compounds. So the first one would be magnesium hydroxide. The second one is potassium nitrate. So it's very important to just ignore how many nitrates we have on the left or how many magnesium we have or how many hydroxides we have on the left. It's just, you have to make sure your ionic compounds that you're making is making sense. So you have to watch for their charges because anytime we write an ionic compound, we have to watch for their charges. If you don't know how to put together these ionic compounds, my suggestion is to look at my video that I'll be tagging over here. I've made a video before that it explains how these ionic compounds are formed and how you can put their formulas together. So first thing is to just write the products that they make sense in terms of chemistry, that it's a correct formula, and ignoring the fact that there is like 2 nitrate ions on the left or 1 hydroxide ion on the left. And then second step for us is to balance these equations. So to do so, we end up getting 1, 2, 1, 2 for our coefficients. And then next is to figure out the state symbol. So we have to take a look at that solubility table to figure out who is the precipitate and who is the aqueous form. So this way we figure out these two are in the aqueous form, but then this will be our precipitate and this is still aqueous. So this is considered as our molecular equation. So in order to write the ionic equation, we have to know that every time you have an aqueous solution, what happens to it is that as soon as they're in the aqueous form, basically their ions are dissociated from each other. So you can separate these two ions. I also will tag another video over here just in case you don't understand why this is happening to show you how these ions are dissociated. So I'll be tagging it over here. So in the first one, magnesium nitrate, it will be dissociated into magnesium 2 plus and 2 nitrate minuses. So the subscript 2 underneath NO3, also it's the charge of magnesium 2 plus, but it also indicates how many nitrate ions we have. Now for the next one, the 2 behind KOH applies to both potassium and hydroxide. So we end up getting 2 potassium positives and 2 hydroxide negatives. However, on the right-hand side, we have a solid. So solids are not soluble, so they do not dissociate. So they stay together in the solid form when we're writing the ionic equation. So we keep it the way it is. And then we end up getting 2 potassium positives, 2 nitrate negatives. Now, for writing the net ionic equation, we have to cancel the repeating ions. So as you can see, the potassium positive and nitrate, they both are repeated on both sides and they're exactly in the same amount. So these ions are considered as spectator ions. So basically what it means is that they're not really reacting over here. They were just there in the solution and they remain in the solution. Nothing is happening with them. So the reason this double replacement is a reaction is because there's a precipitate being formed. And the precipitate is formed because of magnesium and hydroxide and not because of any other one. So that's why we call them spectator ions. So for our net ionic equation, that's basically the equation that shows how that precipitate is formed. So it's basically the remaining ions that they're not canceled out. So it's magnesium 2 positive plus 2 hydroxides forming magnesium hydroxide solid. And this is our net ionic equation. All right, so let's take a look at another example. So again, we're given 2 ionic compounds, so we have to do the double replacement, putting the formulas together in the proper way so that it makes sense based on their charges. So we end up getting these 2 products. Then we have to balance the equation. And then last is for us to find the state symbol. So based on the solubility table, we will realize the first one is aqueous, second one is aqueous. This is our precipitate, and this will be also aqueous. So far we have the molecular equation. Now the ionic equation. As we said again, anytime you see an aqueous solution, you have to dissociate them. So we end up getting 3 lead 2 positives, 6 NO3 minuses. For the next one, we get 6 Na positives, 2 phosphate ions. And then for the solid, we don't separate it. And then again, 6 sodium positives, 6 NO3 minuses. And now to get it to the net ionic equation, we have to cancel the spectator ions. So the repeating ions, which would be these. They're exactly matching in number. Also, always watch it. If you're writing these equations and you don't see them matching, that means there's something wrong that you've done in the question. So go back and make sure you found the correct number of each ion. Otherwise, they cannot be unbalanced. You have to have the same amount of spectator ions on the left as you have on the right-hand side. So these are the spectator ions. And then our net ionic equation will be for the formation of the precipitate, which is 3 lead 2 positives plus 2 phosphate ions, giving us lead 2 phosphate. And that's our solid formed. All right, so thanks for watching. If this video helped you, please like it and subscribe for more. I'll be posting more frequently, and your support means a lot to me. Thank you very much. See you in the next video, hopefully.